For this series of examples, I'm just going to put up a bunch of integrals and focus on the strategy that we would use to evaluate them. Maybe do one or two steps, but not work all the way through it. So this just to get the idea of, okay, how would I think about this integral? How would I strategize coming up with my method of solution? So here's the first one. And if I look at this, I see a bunch of natural logs. So natural log, you can kind of think of, usually it's either integration by parts or substitution. And when I'm thinking about a substitution, I'm going to think about the derivative. So the derivative, if u equals natural log, the derivative is going to be dx over x, right? So I would have to be looking for du, which is dx over x. And it turns out, yeah, I have one right there, right? So I can try that. U equals natural log of x, du equals dx over x. And so what's going to end up with is u in the top here, du, that's my du, and then square root of 1 plus x squared, u squared, right? So this now becomes a pretty easy, again, another substitution, u substitution, but we've already used u. So I can see in the bottom, I've got a u squared, and then I've got a u du. So I would probably try, say, w equals all that bottom stuff. dw is 2u du. So this would end up being like 1/2 dw over square root of w. Okay? And from there on. So back. Now notice that this became a pretty simple problem because I also had this natural log in the top. If I had something like this, I could do the same thing. And in fact, that would be what I would want to do, because if I don't get, what am I going to do with 1 plus natural log of x squared quantity squared, right? I don't know what to do with that. That's a mess. So I can make the same substitution. In this case, I end up with this integral, which is a more difficult integral to do because it's not a simple u substitution. This then would be a trig substitution, right? So just kind of recognizing that and thinking about that. In both cases, my first step is the same, but I come up with a different integral, a simpler integral that is still, I still have to go ahead and evaluate. So I'm just going to put this as trig sub. What would be my trig sub? This would be theta. Obviously the square root is here. So I'm going to do u1, and I would do u equals tangent theta and go from there. Okay. There we go. So let's look at another example. And these are all just random examples that I pulled from section 7.5 of the book. All right, this is a rational function, right? So rational function, I want to go ahead and use partial fractions if possible. But first of all, I don't actually even need partial fractions because there's not anything to break up in the denominator, but the numerator is of order t and the denominator is of order t. So this is not a proper fraction. So technically what I should be doing is dividing, right? So I'm going to divide 1 plus 12t by 1 plus 3t, right? 3t, 12t is going to be 4, right? So then this would be 4 plus 12t, subtract, I get minus 3. So then I can rewrite this as 4 plus or minus 3 over 1 plus 3t dt, right? This one, integrate just 4t. This one is going to be a natural log. Oops. Next example. Oh, this one's a little evil. So this one is I just wanted to make sure you guys had seen one of these. This is, if you think about that strategy for integration, this is actually in that fourth try something else because none of the stuff that we have actually works, right? Forgot the dx. You don't have a UDU. You can't use any trig identities the way it is because of the fact that there's nothing squared, right? We all of our trig identities, it's either sine squared, it's got sine squared, cosine squared, or maybe sine 2x or something like that. There's nothing really to work with here. So this is a tricky integral, but you will occasionally see stuff like this. And so at the end, like try something crazy. It's not really that crazy, but it's sort of like, let's add something new. So what I want to do in terms of adding new here is I'm going to multiply top and bottom by something, but by what, right? So especially the bottom, because the bottom, I want the bottom to be as nice as possible. So I've got 1 plus cosine x here. If I multiply this by 1 minus cosine x, then I will have 1 minus cosine squared, which becomes sine squared. So that's the strategy here with some of these. See if you can come up with something, and you don't see these very often, but it's good to at least have seen an example of it. So when I multiply this, of course, the cross terms cancel. I end up with minus cosine squared x. The top I have to be careful of, right? The top, the cross terms don't cancel. Top's a bit of a pain. But this guy is equal to sine squared, right? So what this becomes, I'm going to rewrite it. It becomes this. And then I break this up, right? By the top, I can break it up into 4 pieces. So I've got 1 over sine squared and 1 over sine, right? Because I've got sine over sine squared. I've got cosine over sine squared. And I've got cosine over sine. Okay. So what about these? Whoops, dx in there. So this is cosecant squared. That's easy. That's the antiderivative of negative cotangent. This is cosecant, which is kind of a pain, but it's like secant. It's negative cosecant theta plus cosecant x plus cotangent x. I realized later I didn't put that on your chart, so maybe write it on the chart. But it's the same pattern as secant. This and both of these guys, of course, you can do with u substitution. U equals sine, du equals cosine. Okay. So I'll stop there and then I'll do another video with a bunch of other ones.